From our tiny blue planet, we look up at the night sky and wonder what lies beyond. Our understanding of the universe is shaped by the view from this one small world. Yet astronomers have pieced together a remarkable picture of the cosmos and our place within it. On a clear night, the human eye can see around 3,000 stars, several planets, and the pale glowing band of the Milky Way. But this is only a tiny fraction of what is out there. Most of the universe remains invisible to the naked eye. The sheer size of the universe is beyond everyday experience. Earth is a mere speck in the solar system, and the Sun is just one of 200 billion stars in our galaxy. Our galaxy is one of more than 100 billion galaxies scattered across the cosmos. To make sense of these vast distances, astronomers use special units. A light year, the distance light travels in 1 year, equals almost 6 trillion miles. The nearest star, Proxima Centauri, is over 4 light years away. Most stars are hundreds or thousands of times more distant. Zooming out further, our Sun lies within the Orion arm of the Milky Way, about 26,000 light years from the galactic center. Our galaxy stretches roughly 100,000 light years across, a vast spinning disk of stars, gas, and dust. The Milky Way is just one member of a small cluster called the Local Group, which contains around 50 galaxies spread across 10 million light years. Beyond that, galaxy clusters merge into enormous chains called filaments, surrounding vast, empty regions called voids. The most important tool for exploring the cosmos is the telescope. Invented in the early 1600s, modern telescopes use enormous mirrors many yards across to collect far more light than the human eye, revealing objects billions of light years away. Most major telescopes are placed on high mountain peaks or in deserts to get above the clouds and turbulent atmosphere. The twin Keck telescopes on Mauna Kea in Hawaii use 10-meter mirrors and computerized adjustments to capture incredibly sharp images of deep space. But visible light is only part of the story. The universe also radiates radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays. Each type of radiation reveals different secrets, from newborn stars hidden in dust clouds to the echo of the Big Bang itself. Radio telescopes use giant metal dishes to detect signals from interstellar gas clouds and distant galaxies. The Very Large Array in New Mexico combines signals from multiple telescopes to create sharp images of celestial radio sources that would otherwise be impossible to resolve. Infrared telescopes detect heat radiation from objects too cool to glow in visible light. High-energy telescopes orbiting Earth observe ultraviolet, X-ray, and gamma-ray radiation from the most violent events in the universe, like exploding stars and black holes. Despite having only a snapshot of the heavens from a single viewpoint, humanity has mapped the cosmos from the moon just 1 light second away to galaxy clusters billions of light years distant. Every new telescope opens another window on the universe, revealing wonders we never imagined. Every spacecraft must begin its journey from a launch site on Earth. Most launch sites are located as close to the equator as possible, where our spinning planet gives rockets a speed boost that helps them reach orbit more efficiently. The most famous launch complex in the world is Cape Canaveral on Florida's Atlantic coast. Home to NASA's Kennedy Space Center, it was the departure point for the Apollo moon missions and over 100 space shuttle flights. Its massive vehicle assembly building prepares rockets for their journey to the launch pad. The largest launch site on Earth is the Baikonur Cosmodrome in the deserts of Kazakhstan. Operating continuously since 1957, it launched the first human into space, Yuri Gagarin, aboard Vostok 1 in 1961. Rockets here are assembled horizontally and pulled to the pad by powerful trains. Europe launches its rockets from Kourou in French Guiana, the closest major launch site to the equator. Japan uses Tanegashima Space Center on a southern island. From these scattered launch pads around the world, humanity reaches for the stars. To reach orbit, a spacecraft must overcome Earth's tremendous gravity accelerating to speeds of several miles per second. The only vehicles capable of this are rockets, which work on the simple principle of reaction. Fuel and oxidant mix, ignite, and blast exhaust at incredible speed, pushing the rocket in the opposite direction. Most rockets use a multi-stage design, first proposed by Russian visionary Konstantin Tsiolkovsky in 1903. Each stage has its own fuel tanks and engines. As each stage burns out, it is jettisoned to reduce dead weight, allowing the next stage to push the remaining rocket even faster towards space. NASA's Space Shuttle, which first flew in 1981, was designed to make spaceflight more affordable. The system combined a large plane-like orbiter with an external fuel tank and 2 reusable booster rockets. It served as a satellite launcher, repair vehicle, and orbiting laboratory. Despite its groundbreaking design, the shuttle proved expensive to operate and suffered 2 tragic accidents: Challenger in 1986 and Columbia in 2003. These disasters led to the shuttle's retirement after 30 years of service. Russia's Soyuz spacecraft has been in use since the mid-1960s, making it the longest-serving crewed vehicle in history. It consists of 3 modules: an orbital module for living, a re-entry module for returning to Earth, and a service module carrying engines, power, and solar panels. Unlike the Space Shuttle, Soyuz is not reusable. The service and orbital modules burn up in Earth's atmosphere, and only the small re-entry module returns safely to the ground, slowed by parachutes and cushioned by retro rockets firing just before touchdown. The future of reaching space is being shaped by commercial companies. Spaceship One made 3 suborbital flights in 2004, and companies like Virgin Galactic use carrier aircraft to take smaller rocket planes to the edge of space. Others are developing fully reusable rockets. From the thundering launch pads of Cape Canaveral to the desert plains of Baikonur, humanity's quest to leave Earth has driven some of the greatest engineering achievements in history. Every rocket that lifts off carries with it our deepest desire to explore the unknown. Once a spacecraft reaches the edge of space 60 miles above Earth, it must achieve incredible speed to stay there. A stable orbit requires the vehicle to move so fast that its tendency to fly straight into space is perfectly balanced by Earth's gravitational pull. 8.5 minutes after launch, the Space Shuttle's engines cut out, leaving it in low Earth orbit at around 210 miles altitude. Moving at 17,400 miles per hour, the orbiter can deploy satellites directly using its robot arm. The Hubble Space Telescope was placed into orbit this way and serviced multiple times by the shuttle. Each visit boosted Hubble into a higher orbit to counteract the slow drag from Earth's thin upper atmosphere that gradually pulls satellites back down. Satellites destined for higher orbits are fitted with their own small rocket motors called payload assist modules. These fire once the satellite has safely separated from the launch vehicle, boosting it from low orbit into its correct position thousands of miles above Earth. During launch, satellites are protected inside aerodynamic shells called fairings. Once in space where there is no air resistance, the fairing splits open and falls away, revealing the satellite inside. The satellite then fires its own engines to reach its final orbit. Satellites can be placed into many different types of orbits depending on their mission. In low Earth orbit, spacecraft circle the planet in just 90 minutes. GPS satellites orbit at 12,400 miles, taking 12 hours to go around once. At a very precise altitude of 22,236 miles, satellites orbit exactly once per day, keeping pace with Earth's rotation. This geostationary orbit lets communication satellites hover permanently over the same spot on the equator, watching an entire hemisphere at once. Polar orbits carry satellites over the north and south poles, allowing them to scan nearly every part of Earth's surface as the planet rotates beneath them. These orbits are perfect for weather satellites, spy satellites, and mapping missions. At special points in space called Lagrangian points, the gravity of the Sun, Earth, and Moon combine to create stable parking spots. The L1 point between Earth and Sun is ideal for solar observatories, while L2 on the far side is used by deep space telescopes like Herschel. The thousands of satellites launched over the decades have created a growing cloud of space debris. From tiny paint flecks to entire rocket stages, this orbital junk travels at incredible speeds. Even a chip of paint once struck the Space Shuttle Challenger, creating a visible crater in its window. Supply missions to the International Space Station involve precise orbital rendezvous 210 miles above Earth. Soyuz capsules ferry crews while unmanned vehicles like Russia's Progress and Japan's H-2 transfer vehicle deliver equipment and supplies. From low Earth orbit to geostationary heights and the distant Lagrangian points, humanity has filled the space around our planet with an invisible web of satellites. These orbiting machines watch our weather, guide our navigation, connect our communications, and peer deep into the cosmos. For most of the past 4 decades, a succession of space stations has orbited Earth. A few hundred miles above our planet, these orbiting outposts provide a home and workplace where astronauts can live and carry out research for months at a time. The first space station was the Soviet Salyut 1, launched in 1971. Small enough to be sent into orbit in one piece, it housed a crew of 3 for just 28 days. The American Skylab followed in 1973, hosting 3 crews for up to 84 days each. A total of 7 Salyut stations orbited Earth between 1971 and 1991. Each generation stayed in space longer, with Salyut 7 occupied for 816 days. Its 2 docking ports paved the way for a new kind of station built from connected modules. The first truly successful space station was Mir, occupied almost continuously from 1987 to 2000. Constructed by adding new modules to the original core over 10 years, Mir eventually consisted of 7 connected sections providing living quarters and working areas. Mir set incredible records. Cosmonaut Valery Polyakov lived aboard for over 14 months straight, the longest single stay in space in history. 11 space shuttle missions also docked with Mir, marking the first major cooperation between American and Russian space programs. The largest space station ever built is the International Space Station, or ISS. A collaboration between 16 countries, it orbits Earth 15 times a day at an altitude of about 240 miles. Construction began in 1998 with more than 100 parts delivered in over 50 launches. Building the ISS required astronauts to complete more than 140 spacewalks to install parts and carry out repairs. The station was assembled piece by piece in the vacuum of space, one of the greatest construction projects in human history. Inside, the ISS has the living space of a 5-bedroom house, divided into habitation and work areas. Astronauts see the sun rise and set every 90 minutes as they orbit, but they follow a regular schedule of 9-hour working days, 5 days a week. The station includes 3 major science laboratories: Destiny from the United States, Columbus from Europe, and Kibo from Japan. Scientists conduct experiments in biology, physics, and materials science, taking advantage of the unique, weightless environment. The Canadarm2 robotic arm, with 7 motorized joints, moves equipment around the station and supports astronauts during spacewalks. Massive solar arrays spanning over 32,000 square feet generate 80 kilowatts of power to keep everything running. Crews of 6 astronauts from around the world live aboard the ISS for months at a time. Their daily routine includes exercise on treadmills and cycling machines, conducting experiments, maintaining the station, eating packaged meals, and sleeping in bags strapped to the walls so they do not float away. From the cramped interior of Salyut 1 to the football field-sized International Space Station, humanity has maintained a continuous presence in orbit. These stations have taught us how to live and work in space, preparing us for the even longer journeys that lie ahead. Spacewalking, or extravehicular activity, means moving outside your craft in the vacuum of space. Of the 500-plus astronauts who have been into space, only about 200 have experienced the thrill and danger of working outside their spacecraft. The first spacewalk lasted only 10 minutes. On March 18, 1965, Soviet cosmonaut Alexei Leonov squeezed through his airlock and floated into the void. His suit inflated dangerously, and he had to release air pressure before he could squeeze back inside his Voskhod spacecraft. Just 3 months later, American astronaut Ed White became the second person to walk in space. Using a gas-powered handgun to propel himself, he moved freely outside his Gemini 4 spacecraft and famously called his return inside the saddest moment of his life. Spacewalking astronauts wear pressurized suits that provide their own Earth-like environment. The outer layer combines waterproof, bulletproof, and fire-resistant fabrics. A life support backpack controls temperature, pressure, and oxygen. Modern suits are used about 25 times before replacement. Astronauts stay connected to their craft by short mountaineering-style tethers. Only a handful have ever been completely free. In 1984, Bruce McCandless flew 320 feet from the space shuttle using a jet-propelled backpack, the first untethered spacewalk in history. Before every spacewalk, astronauts spend hours preparing. They breathe pure oxygen to remove nitrogen from their blood, then slowly reduce pressure in the airlock over 6 hours. Without this preparation, they would suffer decompression sickness, just like deep-sea divers who surface too quickly. One of the most dramatic uses of spacewalking was servicing the Hubble Space Telescope. Over 5 missions, astronauts corrected its mirror problems, upgraded computers, and replaced cameras, spectrometers, gyroscopes, and solar arrays, giving Hubble decades of extended life. Astronauts have spent over 900 hours spacewalking outside the International Space Station. The longest ISS spacewalk lasted 8 hours and 56 minutes. They add new modules, maintain existing structures, and carry out repairs in the harsh vacuum of space. Every tool an astronaut uses outside is attached by retractable strings to prevent it from floating away. Astronauts stay hydrated through a drink straw inside their helmet and check their wrist-mounted checklist to remember each step of their carefully rehearsed procedures. Before any real spacewalk, astronauts practice underwater in a massive pool called the Neutral Buoyancy Laboratory. They work on full-scale models of the actual station parts they will install, spending years training for walks that may last only a few hours. For almost 50 years, astronauts have carried cameras into space. The first was American John Glenn in 1962. Today, astronauts spend about 30 minutes each day taking photographs of Earth requested by scientists, documenting everything from volcanic eruptions to city lights at night. Astronauts aboard the International Space Station have a unique view of Earth. Unlike satellites that look straight down, astronauts can photograph in any direction, swapping lenses and tracking features like thin dust clouds, ocean glints, and city lights at night. 10 windows on the ISS allow astronauts to look down on our planet. The Destiny Laboratory window was specifically designed for photography, transmitting over 98% of light with zero distortion. The cupola module added 7 more windows for an unmatched panoramic view. Since the early 1960s, hundreds of satellites have been launched specifically to image, measure, and monitor Earth's land, sea, ice, snow, and atmosphere. These orbiting eyes watch over our planet continuously, tracking everything from weather patterns to long-term climate change. The first satellite to transmit pictures of Earth from space was NASA's Explorer 6 in 1959. The first television weather images came from Tyros 1 in 1960. These pioneer satellites launched a revolution in how we understand and monitor our planet. Modern Earth observation satellites like NASA's Terra cover the entire globe every 1 to 2 days. Their instruments measure cloud properties, land temperatures, surface elevation, and reflectance. Sister satellite Aqua studies Earth's water cycle, while Europe's Envisat carries multiple advanced sensors. Satellites use both passive and active sensors to study Earth. Passive sensors detect light and heat naturally emitted or reflected by the surface. Active sensors, including radar and laser devices, emit their own energy and record what bounces back, even penetrating cloud cover to map terrain below. Oceans cover 71% of Earth's surface and have a huge influence on climate and weather. Satellites like JASON-1 and JASON-2 use radar to monitor the exact shape of the ocean surface, tracking tides, sea level changes, and the movement of warm and cold water masses around the globe. By measuring tiny variations in ocean height, satellites can indirectly measure temperature since warm water expands. They also track concentrations of microscopic plants called phytoplankton, which form the base of the ocean food web and influence the amount of carbon dioxide in our atmosphere. Satellites reveal Earth's land in extraordinary detail. They monitor unfolding natural disasters like volcanic eruptions, floods, and forest fires. They spot ancient faults in the Earth's crust and craters made millions of years ago by asteroid impacts, telling stories written in the landscape. Using infrared sensors, satellites can see what human eyes cannot. They distinguish healthy crops from harvested fields, track the growth of cities like Las Vegas over decades, and detect the heat signature of forest fires even through thick smoke. Hundreds of weather satellite images combined together reveal the distribution of human population through city lights at night. This stunning view shows how concentrated human activity is in certain regions, while vast areas of ocean, desert, and forest remain dark and untouched. From the first grainy television image of clouds in 1960 to today's continuous high-resolution monitoring, Earth observation satellites have transformed our understanding of our own planet. They watch our weather, track our climate, map our oceans, and reveal how human activity is reshaping the world. Satellites have revolutionized our ability to monitor Earth's frozen regions. Arctic sea ice covers a vast but constantly changing area, thickening in winter and melting in summer. Year after year, instruments on satellites track its slow but steady decline. NASA's IceSat satellite measures the thickness of ice sheets covering Greenland and Antarctica using precision laser pulses from orbit. The data reveals that both ice sheets are losing mass overall, with glaciers retreating up their valleys and thinning at alarming rates. When massive chunks of ice break away from Antarctic ice shelves, they form icebergs the size of small countries. Satellites track these floating mountains of ice as they drift through the Southern Ocean, warning ships of danger in some of the world's most remote waters. Snow covers vast areas of the Earth and reflects up to 80% of sunlight back into space. By measuring snow grain size and impurity content from orbit, scientists can calculate how much heat Earth absorbs from the sun, a crucial factor in understanding climate change. High above the glaciers and snowfields, Earth's atmosphere extends hundreds of miles into space. This thin blanket of gas is 78% nitrogen and 21% oxygen, with traces of carbon dioxide, water vapor, methane, and ozone that control our planet's temperature. All weather occurs in the lowest layer of the atmosphere, the troposphere, extending just 10 miles above the equator. Satellites monitor clouds, hurricane formations, wind patterns, sandstorms, volcanic ash plumes, and smoke pollution, giving us advance warning of deadly weather events. Hurricane Rita in 2005 was the strongest tropical cyclone ever observed in the Gulf of Mexico. NASA's Aqua satellite captured stunning images of the massive storm as it plowed northwest, its spiral band stretching hundreds of miles across the warm Gulf waters. High in the stratosphere, a thin layer of ozone protects all life on Earth from harmful ultraviolet radiation. In 2006, NASA's Aura satellite observed the ozone hole over Antarctica at its largest ever recorded extent, 10.6 million square miles, caused by chemical pollutants. Satellites also monitor invisible greenhouse gases that trap heat in our atmosphere. Instruments like the Atmospheric Infrared Sounder on NASA's Aqua satellite map the global distribution of carbon dioxide, revealing how concentrations vary by season and latitude across the planet. Water vapor is the only atmospheric gas we can see, forming clouds of tiny droplets or ice crystals. From space, satellites reveal the global distribution of water vapor, showing moist tropical regions and dry desert zones, the invisible engine that drives our weather and climate. Even human pollution is visible from orbit. NASA's Terra satellite has captured bands of thick, gray smog stretching over eastern China, while ship exhaust trails form distinctive streaky clouds over the Pacific Ocean as water molecules condense around the particles ships emit. From tracking Arctic ice to monitoring the ozone hole, from mapping carbon dioxide to photographing hurricanes, satellites give us an unprecedented view of our planet's complex systems. This constant watch from space is essential for understanding and protecting the only home we have.